In this section, we're going to take a closer look at continuity and how it's related to function values and limits. Our learning objectives are explain the three conditions for continuity at a point, describe three different kinds of discontinuities, define continuity on an interval, and then state the theorem for limits of composition of functions and provide an example of the intermediate value theorem. I'm planning to do the first 3 pages of this section in one video and then the remaining pages in another video. So first we'll look at definition of continuity at a point. So if we have continuity at a point, C, it says first of all f of C has to be defined. So there has to be a point C f of C. And the next thing is that the limit as x approaches C for this function exists. That means both sides approach the same value. And then lastly, the value those two sides approach has to be the same as the function value itself. So I can't have these two sides, doing something like this. They instead have to agree with the function. Right? So they all are connected. Right? So those are the 3 requirements for continuity. Notice this last requirement implies the first 2, because if the function value is undefined or the limit doesn't exist, then this third requirement would fall apart because there's no way for them to be equal to each other if one of them is undefined or doesn't exist. Right? So really, that last one is the main one to think about because it captures all 3 together. So continuity at a point can be destroyed if any one of the following conditions fails. So if the function is not defined at C, then the function is not continuous at that point, and my values here should be C instead of A. I'm catching that right now. So maybe the function's not defined there, as in the first picture. Maybe the limit doesn't exist there, as in the second picture, where the two sides are not approaching the same value. Or in the third picture, the function is defined and the limit exists, but they're not the same thing. Right? So these are 3 ways where the discontinuity can happen. So our problem-solving strategy, if we're trying to just decide if a function is continuous at a single point, not on an interval, but right at a point, we would first check to see whether the function is defined there. If the function is not defined, we can just stop and we can say the function's not continuous at that point. If the function is defined, then we'll start to look at the limit. Sometimes we'll want to look at the left-sided limit and the right-sided limit to decide if the function limit exists at that point. If the limit does not exist, then the function is not continuous there and we would stop. If the limit does exist, then we just need to make sure that the limit we find and the function value we found are the same thing. If they're not, then the function is not continuous. If they are, then the function is continuous. So start by checking the function value, then compute the limit, and then just to see if they're the same thing. So what we're going to do is we're going to look for discontinuities, and if we find a discontinuity, then we are going to classify it as removable, jump, or infinite. Jump is fairly straightforward because it looks like its name. There's a jump to get from one value to the other. So that's what jump would look like. Removable is like a hole in the graph. So the two sides connect. Maybe the function value is defined somewhere else, but that's what removable would look like. And then infinite would be like a vertical asymptote. Right? So let's look at these examples and see where the discontinuities are and look at which type of discontinuity we have at each discontinuity. So the first one, f of x equals x minus 3 over x squared minus 9, and we're interested at what's going on when x equals 3. So if we think about this function in factored form, anytime we see these repeated factors that match in the numerator and the denominator, that's indicative of a hole in the graph. And that means we'll have a removable discontinuity. So when you see matching factors in the numerator and the denominator like that, that tells you there's going to be a hole in the graph, and that's a removable discontinuity. Right? So that graph, if we wanted to think carefully about it, it's going to have a vertical asymptote at x equals -3, because that's a 0 of the denominator and it's not repeated in the numerator. There's going to be a hole in the graph where x equals 3. To figure out where the y-coordinate is, we would plug in x equals 3 to the other factors. So we'd have 1 over 3 plus 3, so 1 over 6. So we'll have 3, 1/6 will be a hole in the graph. The denominator of this function is higher degree than the numerator, which means that there's going to be a horizontal asymptote at y equals 0. So this will just keep going that direction. If I plug in x equals 0 to find the y-intercept, I have -3 over -9, so 1/3. And then I'll approach that vertical asymptote. And the graph is going to look like that. I ran out of space to the left there, but that's the idea for this picture, for this graph, right? So there's a removable discontinuity at x equals 3. And they didn't ask about this, but there's also an infinite discontinuity at x equals -3. All right, so most of the time when you have a removable discontinuity, that's going to be the result of matching factors in the numerator and the denominator. You'll also see them sometimes on piecewise functions where you have the piecewise function just redefined at a point, which might be the case here in example B. Let's take a look. So here we have f of x equals x minus 1 for x less than 2. So I'm just going to make a quick sketch of this graph. So x2, it's linear to the left of 2. And let's see, if I were to plug in x equals 2 here, I'd have 2 minus 1. So that's 1. And that tells me I'm going to have an open circle because x equals 2 is not included, but I want to go all the way up to that. Open circle at the point 2, 1. And then linear with slope 1 and y-intercept -1 to the left of that. So that's the first branch. And then let's see, we have just a point. When x equals 2, we want the y value to be 5. So we have this point 2, 5. And then for x greater than 2, we want to use -2x plus 5. So -2x plus 5. If I were to plug 2 into that, I have -4 plus 5. So that's 1. So again, an open circle at 2, 1, and then slope -2 to the right. So a little bit steeper and negative slope. So here we have an example of another removable discontinuity, because this graph would be continuous if we just move that point back down, so from 2, 5 to 2, 1. Right? So since the two sides would match otherwise, we do have removable discontinuity. All right. Example C, we have another piecewise function, and this time it looks like we have two parabolic branches. And I believe we saw these parabolas in an earlier example, but let's just review how we could get this graph. So for me, the easiest way to think about parabolas is to find their vertex. So here I'm going to do the first one. My vertex will be x equals opposite of b over 2a, which is 4 over 2. So x coordinate 2, which happens to be our split point for our two branches. And y would be 4 minus 8 plus 6. And that is also 2. Right? So here we have the vertex for the top line at 2, 2. It's going to be an open circle because x equals 2 is not included, but we are going to go all the way up to that point. So we want an open circle there. And then this parabola is for x's that are less than 2, and it's opening upward. I can also see if I plug in 0, I would have 6. So there's another point. And that's what that side of that parabola will look like. Then for the other side, I will do the same thing. I'll find the vertex. X equals opposite of b over 2a, which is -4 over -2. So also at 2, and then the y coordinate for that vertex will be -4 plus 8 minus 2, and that's 2 again. And so this time this is filled in, and the other parabola is opening downward, and we're supposed to use that for x greater than or equal to 2. So we have that filled in point, and then we'll go down from there. So this time the two sides match up, and the function value of 2, 2 from that second branch matches the limit from either the right side or the left side of 2. So this has no discontinuity. At 2 or otherwise. And then example D is going to look very similar actually to example A that we did. So I have f of x equals, and I'm going to factor this since it's a rational function. That will make it easier to think about, easier to analyze. And so this will factor as x plus 2 times x minus 1. Right, so just seeing this again, I have these two repeated factors. That is going to tell us there's a hole in the graph at x equals -2, and to find the y, we would just picture the reduced form, which would be 1 over x minus 1, and fill in x equals -2. So that's going to give me -1/3. So there's my hole in the graph, and then I also am going to have a vertical asymptote at x equals x equals 1, because that value makes the denominator 0, and it does not make the numerator 0. It's not a repeated factor, it's just a 0 of the denominator. So this graph vertical asymptote at 1, hole in the graph at -2, -1/3, and again the degree of the denominator is greater, so I'll have a horizontal asymptote on the x-axis the y-intercept would be, if I plug in x equals 0, I have 2 over -2, so -1. So this graph will look like this. Right? So we have, this would be a removable discontinuity at x equals -2 and an infinite discontinuity at x equals 1. We didn't see an example here of a jump discontinuity, so what I would like to do is just modify example C a little bit. So suppose instead that we had g of x equals x squared minus 4x plus 6 if x less than or equal to, or sorry, less than 2, just like f was. But instead, for the second branch, if instead of what's listed, we just have -x squared plus 4x without the -2 at x greater than or equal to 2. Let's imagine what that's going to look like. So then our first parabola is going to be exactly the same. So we'll have 2, 2 as an open circle, and we'd have this branch to the left. But the second parabola does not have that down 2 shift. It's going to have the x-coordinate of the vertex still at 2, because opposite of b over 2a is going to be exactly the same. But now the y-coordinate is going to be -4 plus 8, so 4 instead. And it would open downward still, right? But with that change, now instead of no discontinuity like we saw before, now we have a jump discontinuity. At x equals 2. Right, so that's what a jump discontinuity would look like. We have these two branches, and the two sides aren't even close to doing the same thing. All right. Next, we want to look at continuity from just one side or the other. We'll say a function is continuous from the right at a point if the limit from the right is equal to the function value, and a function is continuous from the left at a point if the limit from the left is equal to the function value at that point. Let me just make a quick sketch of maybe a familiar example. So suppose you're thinking about like square root of x. Right? So we would say this function f of x equals square root of x is continuous from the right at x equals 0. We can't talk about continuity at 0 because there's no values to the left of that point, but we can talk about continuity from the right. Okay, so that's one place you might talk about continuity from just one side or the other, is if the domain doesn't even include values to the left. Let me make one more sketch here. Maybe you also could see something like this. Maybe I have a function that does like this and is defined, but then on the other side has a vertical asymptote, right? So something like this, we would say this function, if this is a, this function is continuous from the left at a. If you look back at our previous, the example I just made up here that had this jump discontinuity, we could also say this function here, g is continuous from the right at 2, because from the right, the limit and the function value agree. So hopefully those few sketches help you understand what that definition is saying. If we want to talk about continuity over an interval, we define continuity on an open interval to mean that the function is continuous at every point in that interval. And remember that continuity would require the limit from both directions to be the same as the function value. And if we want to talk about continuity on a closed interval, for the points on the interior of the interval, we would just mean the function is continuous there, but on the endpoints, we would mean continuous from the right for the left endpoint and from the left for the right endpoint. Right? So if we're looking at the function f of x equals square root of 4 minus x squared, and we want to talk about the continuity for that at x equals 2 and negative 2, we would notice that the domain for this function, we would need 4 minus x squared to be greater than or equal to 0. And that translates to x squared less than or equal to 4, which means x has to be between 2 and negative 2. Because bigger than 2 or less than negative 2, when I square it, I'm going to have something that's bigger than 4. Right? So the domain is just the interval negative 2 to 2. Our limit laws would tell us that this is continuous, and we could use direct substitution on all of the values that are in the domain, but on the edges of the domain, we would have to say this is just continuous from the right or the left, depending on which edge we're talking about. So we would say this f is continuous from the left at x equals 2, the right edge of the domain, continuous from the right at negative 2, and we can say it's continuous on the closed interval negative 2 to 2. Right, so they were asking specifically about what type of continuity do we have at the two endpoints of the domain, and then we can conclude that the function is continuous on this closed interval from negative 2 to 2. It might be helpful to look at the graph of that, since that's not a super familiar function. We'd have this parabola, and then we're taking the square root of the y values, right? So let's just quickly look at that graph. So we want square root of 4 minus x squared. I should have talked about the window first, but we already knew that the domain should be negative 2 to 2. Right? And so this is what your graph is going to look like. It almost looks like a parabola. It's not quite, but so defined for x is between negative 2 and 2. And we can see we've got this graph that looks like almost like a parabola, and it's continuous from the right at negative 2 and from the left at 2. Okay, now let's take a look at a slightly more interesting example. So here we're trying to find a k so that this function is continuous on the interval from 0 to 10. All right, well, the first issue is I notice I have a typo here on the second branch. The x's should be greater than 3 and less than or equal to 10. I had that kind of out of order there. So if you think about what's going on, I have some sort of square root function between 0 and 3. And then I have a graph that's linear once I am past 3. So here, the second branch doesn't depend at all on our value of k, right? That's just x plus 1. And so if I think about if I were to plug in 3, I'd have 3 plus 1, and that's 4. So I'm going to have an open circle at 4 for the y coordinate and 3 for the x coordinate. And then that is just going to be linear going up. I shouldn't continue that with an arrow. I want to stop at the point 10, 11. So I'm just going to label this. That stops at 10, 11. Right? So between 3 and 10, I'm using the function of y equals x plus 1. And so I'm going to just have this linear piece. Right? Before that, I have the square root function, but with this factor of k inside, technically that's, let's see, a horizontal compression or a stretch, depending on the value of k, right? So we would have our normal square root function, and then, oops, again, not with an arrow. And I don't want it to be linear, this kind of thing, but then we're going to compress it or stretch it so that we can get these two pieces to connect. Okay. I'm going to just bring up GeoGebra so that you can get a visual idea of what's happening here. So I have this already entered. My first function was the square root of kx for x between 0 and 3. And my second function was x plus 1 for x between 3 and 10. And just so you can see how to input these piecewise functions into GeoGebra, it's really simple. So say I wanted like 2x plus 5 for x greater than 10. I would just enter 2x plus 5 and then a comma, and then put my condition, so x greater than 10. That's how I would enter that. And then it changes it so it looks like this if-then statement, but you can just type it just like that. Right. And if you need a value of k, you just type that in and then a slider automatically appears. So it's pretty nice. Okay, so I have these two that I want to take a look at. Right. And now I've changed the window a little bit here. You can see both pieces. Right. I've got this square root branch and then that linear branch. And if I slide my value of k, if I'm making it less, it looks like that's not the way I want to go. If I'm making it greater, it's getting closer, and I just want these two to match, right? That's what I'm aiming for. So it looks like GeoGebra's estimate is something around 5.4. So let's see how close it was. If we think about limits here, what we want is the limit as x goes to 3 from the left equal to the limit as x goes to 3 from the right. And both of them to be equal to f of 3. F of 3 we already computed, that's 4, right? And it was already the case that the limit for x going to 3 from the right was going to be equal to f of 3 because that's the way that second branch was going to work, right? It's linear and 3 was included in the domain for that branch, so that will happen. No problem. It's just we need to worry about the limit as x goes to 3 from the left. We want to make sure that that is also 4, right? And that's what we'll need to manipulate this k value to achieve. Right? So what we need is the square root of k times 3 to be 4. Because the square root of k times 3 is that limit from the left as x approaches 3, right? So we need to solve this for k. If I square both sides, I'll have k times 3 equals 16. And that's going to give me k is 16 over 3. 16 over 3, that's 5 1/3. And that's really close to what we saw it looked like from GeoGebra, right? So looks like the k value we need is 5 1/3. All right, so that's where I'll stop with this video, and then we'll look at the rest of this section in the next video.